Welcome to another RDWorks Learning Lab. In the last session we managed to, I think, fairly conclusively prove that there's some strange things going on with lenses that we haven't really been aware of. Now, not only are there some strange things been going on with lenses, I've been rather brutal in the way in which I've been treating lenses to prove that point, that there's some strange things going on. It's going to be a little bit difficult for lens manufacturers to comprehend this, I think, but at the end of the day, facts are facts. I can only demonstrate what I find. As I said last time, I'm reverse engineering this process. I'm not predicting what's going to happen at the job. I'm seeing what's happening at the job and actually predicting what's happening in the lens. So that's a completely different direction of analysis. Now today, what we're going to do is see if we can pursue that a little bit more. And to do that, we're going to use my compound engraving lens. Now the compound engraving lens, I love it. I spent a long time trying to discover the magic combination that produced the best and smallest possible burn spot. That's not the same as this spot size, this theoretical spot size that everybody keeps talking about. That is fantasy, because we're never going to be able to see anything like that. And if you see anybody using those numbers to calculate their resolution, picture resolution, then yeah, just laugh at them. My compound engraving lens is capable of fairly predictably getting down to about a 0.1 burn dot on quite a few materials. On certain very, very hard materials like laser tiles, I've been able to get down to about 0.06 millimeters, but that's an exception. I'm looking at this as being a 0.1 lens, but it's got such a short focal length that technically it ought to be pretty close to this theoretical half of nothing, but it's not, and that's always puzzled me. The other thing that's seriously puzzled me about this lens is that although it's got an incredibly short focus, which technically means all the energy is being focused onto the surface of the job, it can still cut 6mm thick acrylic without too much problem. How is that possible? It just doesn't make sense. Well, it didn't make sense until I've come up with my theory of how lenses work. And now all of a sudden it begins to make perfect sense. Replacing this 1.5-inch PVD lens with a rather special 1.5-inch PVD lens that I've modified. Now, is that going to help or hinder the performance of this compound lens? I think it's going to help this lens perform even better. In the first instance, what we've got to do is be logical about this, and we've got to prove that there is a change. And the way that we're going to do that is, first of all, we're going to set the focus of this compound lens up and find out what its focus point is, and then we're going to test it with one of my test blocks to find out what its penetration ability is. In other words, what its cutting ability is. We're going to produce a standard for this lens to start with before we go any further. Now, before we start the focus test, I thought you might be interested in something that's rather different. If you note when you set the parameters, there's always something called default, which you never use. If you write a program and then tick the default settings, it will ignore your program, and what it will do, it will use the speed that has been set by this button here on the machine and the maximum and minimum power that you set on the machine. Now, if you take a look down here, you'll see that all my parameters are set to 0. Well, that's silly. I'm not going to do anything, am I? Well, yes I am, because I've set the default settings, and now what happens is I've got a power of 20% and I've got a speed of 400. So every one of these parameters in here would be running at 420% power. So if I want to change the parameters easily and quickly for everything, all I've got to do is swap it on these two buttons. I know that my nominal focus is around about 11 millimeters for this lens, somewhere in 10.5 and 11. So what I've done, I've set the gap under here to 7 millimeters. So 7 millimeters is my starting point, and we go and look for the focal distance on this lens. Seven, 8, 9, 10, 11, as I predicted. 12, 13, 14, 15, and you can see how quickly it goes in and out of focus. Now I'm going to reuse this block slightly forward of that previous test because there's almost nothing on it. So the first thing we must do is set this up to 11 millimeter focus. You see what I mean? There's no confusion between the front set and the rear set. Now I think you can see for a compound lens that's supposed to have a very short focus and all of its power right onto the surface, it's a pretty good cutting lens. Okay, so what we're going to do, we're going to just find what the real focus is with a piece of card. And what I've got here is a slope gauge which I use, which is marked off in 0.1 of a millimeter increments. Now, as it says on this piece of paper here, the nominal focus for this is 10.5. This lens is very sensitive to focus, so we're going to set that to 11. But I've got a fairly thin line, so we'll now change it to 11.3. And 11.3 is getting better, and now we're getting some nice dots. So we go and look at those under the microscope shortly, and we might do one further test with those settings, 11.9 and 41%, and that will be on a piece of HDF. Now we might have to change the settings to do it on HDF. It's not very dark. It's very deep, but not very dark. So we've got several reference tests that we can refer back to when we change this lens over. So we take that nice 38mm lens out, and we'll put my dodgy 38mm lens back in its place. 7mm, the same as we did before, and we'll find out how the focus has changed. So I decided to go a little bit further than what I proposed in the workshop. I found that I'd actually got two lenses here with holes in. One of them happened to be this lens at the bottom of the compound lens kit, and the other one was the top lens out of the compound lens kit. Now, what you saw me do in the workshop was add that one in place of that one. But subsequent to that, what I've done, I've added that one to the top one, and then I've done that. We've put them together. So we've got four possible combinations that we can look at to see how the effect of removing the centre of the lens, the so-called cutting part of the lens, according to me, affects the result. So without involving you with all the tedious work stuff, I've just documented the results that I've got. At the top here we can see this blue line, which is the normal lens, i.e. good 38 and a good 63.5, what I would normally use for photo engraving. We put a hole through the middle of both lenses and we get this yellow line, which is rather surprising because, hey, I thought I'd removed the cutting ability from that lens, so its ability to cut or penetrate into acrylic has hardly been affected by those two holes. Very surprising because that's what I thought I'd removed. So when I replace the top lens with a holy lens and leave the 63.5 in place, I do get an effect on the cutting result, because obviously the top lens with a hole in it is affecting the bottom lens. But more significantly, when we put a holy lens at the bottom and a good 38mm lens at the top, we get quite a serious degradation in its cutting power. Now this lens was never intended as a cutting lens, it was always intended as an engraving lens. So this is just an exercise to see what happens when we put holes in lenses and supposedly affect their cutting ability. Now affecting the ability to focus is one of the things that I had expected. So here's the blue line again for the normal lens. Now whether we use the top 38mm Holy lens or both lenses with holes in it, you'll notice that we've increased the focus range. In other words, the focus is not as sharp as it was before. It's still at approximately 21mm where it was before. But the surprising thing is when we have the 63.5 sitting at the bottom with a hole in it, it really does have a significant effect on the focal distance, because that has come down from 21 to 16. Now here's what my dot test looks like. There are 3 lines on here normally. There are some dashes up the top here which we're not interested in. What we're more interested in is these dots here, because these dots here, they're very difficult to achieve. This is a 254 ppi, pixels per inch, pattern that I'm copying here. And each one of these black blobs here is a pixel. Now a pixel is 0.1 millimeter wide, and this pattern is 0.1 pixel, 0.1 gap, 0.1 pixel, 0.1 gap. And as you can see, we've got a fairly consistent pattern there that we get from the normal compound lens when it's set up properly. Now this is set up on card. The problems with these dots, as you can see, they're not really dots, they're dashes. It's incredibly difficult to get dots with a laser machine because it doesn't produce dots. What it does, it turns the beam on and off. And let me just explain to you how and why it's difficult to get these dashes, especially down at 0.1 millimeter. Now here we've got a simplified model of our machine, the controller, the high voltage power supply and the tube. And here we've got a line of pixels. The ones with the crosses in are black pixels and the ones without are obviously white pixels. Now when you load a bitmap into RDWorks and send it down to create a program, the controller knows exactly where each of these pixels are, especially depending upon what speed you choose to run at, because it has got to switch the tube on and off to match the rate at which these pixels pass it by. So the controller can respond virtually instantly, let's just say 1 microsecond, which is electronic switching speeds, and the signal goes to the high voltage power supply. Now the high voltage power supply is a bit of a lazy beast. If you go and check up on any of the specifications, you'll always find that the power supply is specified as 1 millisecond response time or less to reach 90% of the demand value that you're asking me to deliver. If we put a power signal in here which is 50 watts, it means after 1 millisecond we're going to get 45 watts of current flowing through the tube, but it's taking a millisecond for that to happen. And the reason why it takes a millisecond for that to happen is because before the current can flow through the tube, we have to raise the voltage of the tube up to 24,000 volts to make an ionized pink beam in the tube that can carry the current that we're asking for. So every time you switch the tube off between these pixels, it dies and switches off and kills the 24,000 volts. Okay, so we don't have a beam in there any longer, so we can't carry this power. So this tube is continuously switching on and off, but it can only switch on and off at this sort of speed. Now, if it happens to be as bad as 1 millisecond, 1 millisecond means that it's got to switch on in this period here, which is 1 millisecond, and then it's got to burn a pixel. and then it's got to switch off, and let's assume it switches off instantly, but then the controller knows it's got to immediately switch back on again because it's going to take a millisecond to bring back up to burning power again. So we've got this serious delay problem in the system. And if it really is as bad as 1 millisecond is 1,000 pulses per second. So that means we can only put down 1,000 dots per second. And if we've got 254 ppi, pixels per inch, it means we want to put down 254 dots per inch. Now, in real terms, what that means is that each pixel is 0.1 of a millimetre, and that means every millimetre has got 10 dots. So if I run at 100 millimetres a second, I produce 1,000 hertz. So I can only ever run this machine at 100 millimetres a second to get 1,000 dots per second out of this tube. Now in reality, most power supplies work at a different speed than that. They can probably work twice or maybe 4 times as fast as that. But something else strange then starts to happen. So when we run slowly, we get fairly clean switching like this. But once we start running fast, what we tend to get is switching that looks more like this, okay, where you're tending to even out the squareness of the signal into a smoother signal. And what that means is you're not actually putting a complete pixel of burn down. What you're actually doing is just going blip, blip, right in the middle of the pixel, which is absolutely amazing for what we want to do with a glass tube, because we can play with the balance of response time and speed to get dots. Now, in the case of an RF tube, where you don't have this response time problem, everything happens instantly, then because everything happens instantly, when you switch on the beam switches on right at the start of the pixel. And so if you've got a beam which is 0.1 of a millimetre wide and we've got 0.1 millimetre pixels, then what happens is the instant the beam switches on, we've got a pixel which gets burnt. And the beam stays on for the duration of the pixel, and by the time it finishes the pixel, we've got half a beam hanging out the other side as well. So we don't actually burn a square, we burn a sausage. And then, of course, this gap in the middle here is 0.1. But hang on, the next beam has been told to start just here and finish just here. So we get another sausage. And we don't get gaps between the sausages. And that completely destroys the printing capability or the photo printing capability of the system. And that is one of the reasons why an RF tube is pretty abysmal at photo engraving. And they do all sorts of tricks with the software that they use for photo engraving to try and make it better. But it will never be true photo replication. We can get true photo replication with our glass tube machine because we have this very strange characteristic that we can play with if we work the speeds and the powers correctly. So back to my picture there. It looks as though we've got sausages here, but they're not the same sort of sausages that you see there. They haven't closed up the gap between the pixels, you'll notice. But that's because these are 0.1 dots from a 0.05 wide beam. So the beam is narrower than the pulse width. So we've actually switched on and off we've balanced the power here so that we're switching on and off quite cleanly on the edges of the pixel. We've played with the parameters here so that we're getting a nice sausage on the top of each one of these pixels, like that. And if we had a wider beam, we would have 0.1 dots. Who said this stuff was simple and straightforward? Okay, so that's the normal performance that you'd expect out of a compound lens. That's why I've been through all this explanation here to explain how and why we get these rather strange shaped pixel burns here. Okay, ideally we'd like them to be 0.1 diameter and 0.1 spacing between them. So let's just see what we've been able to produce with our junk lenses. Here's our standard compound lens performance. Here's what happened when we replaced the lower 63.5 lens, both on card and on MDF. Here's what happened when we replaced the top lens on card and MDF. And here's what happened when we replaced both lenses on card and MDF. Now, I think we would be able to get these a little bit darker by fiddling around with the power a little bit. These are round dots, but weak. These are round dots, a little bit stronger. And in fact, they look quite nice dots, those. These would work very well. They're 0.1 sausages, about 0.05 wide. Here we've got dots which are a bit inconsistent, and they're around about 0.1. These again are quite round dots, they're not sausage dots. It's rather strange that, isn't it, that we've managed to get round dots on most of these as opposed to our sausages. So I think that on balance I ought to try one or two of these combinations at proper photo engraving with maybe my Foxy pattern. I think it's worth a try to see just what happens in the real world. Well, it's doing a reasonably enough job. It looks just a little bit fuzzy in the darker areas, but I mean some of the definition is pretty good. But this is using the absolutely abysmal 38mm lens with a hole through the middle. And we'll just take that lens out to show you what we've been using. And there it is, look, big chip off the side, big lump out the middle. Look at it. That shouldn't be engraving anything, should it? As you can see, it's done a half reasonable job. I mean, most people would be very, very happy with that as an engraving lens. Me, not so. Look at the eyes, and the nose. You can't see the nostrils. You can't see the definition in the eyes. When we compare it to that one, you'll see what I mean. So we have slightly destroyed the engraving characteristics, but nothing gross. So what we've got in here at the moment is our 38mm no focus lens, which we tested in the previous session. Now this was originally an 1.5" focal length lens, and I've removed all the outer part which does the normal focusing to get it to a 38.1 focal length, and I've just left this central 3mm section in here. And here it is as I drop down below 6mm to 37mm. As I go down further away from the nominal focal point, I've found another focal point. And I think that conclusively proves my theory that there is a spike of projecting focus way beyond the nominal focal point of lenses. After my rather quick and dirty test to see whether or not something was happening below the focal point, as I was half expecting, i.e. another focal point below the nominal 38mm focal point, I thought I'd better do a slightly more scientific approach to it because, yeah, I was quite excited to find that, but it doesn't tell me everything that I want to know. So what we're going to do now is a variation of my penetration test, and we've got 10.5 of the lens buried inside the nozzle. And so if I set that to 17.5, or that's the total focal length now, 38mm, which is the focal length of this lens before I modified it. Remember, this lens has only got 3mm of good 38.1 lens left. So it isn't very good at focusing. And to try and find out if we've got something happening below the focal point, what I've done, I've modified my standard depth penetration test. We should find a set of penetrations happening across here, but every one of these penetrations is exactly the same. They're all 300 milliseconds of pulse, so they're the same power and the same pulse length, but the only thing that's changing is the depth of the table. This gap is going to grow by 2mm every time I produce a new line. There we go. I'm trying to work out what this actually means. That's a puzzling set of results. I've checked the program and there's absolutely nothing wrong with the program. All the pulses are the same length and the depths go down by 2mm at every step. Let's try the same thing with a piece of card, shall we? Well, there's the pattern on the front of the card. We'll take a look at the pattern on the back of the card. Well, we shall have to go and look at those under the microscope and measure them, but I think you can clearly see that they are, again, what we expect. They're starting off big and then they're gradually getting smaller and smaller, and then they get a little bit bigger again as we probably pass through the focal point and start coming out the other side. Okay, so I've measured the progression of these burn dots, and here's the result that I came up with. Here's our 38mm nominal focal point, and then as you see we appear to have another focal point here at 53. Okay, now look, it is about 0.7 diameter. That's quite a big diameter for a focal point, but what you'll have to remember is it's not really the proper focal point. What it is, it's the diameter of a burn, a 300 millisecond burn, which not only includes the central core, which would be a very small point, but it also includes a lot of the low power part of the outer part of the beam. This is piece of support evidence, if you like, number one. And then we've got this rather strange piece of evidence that we've got to make sense of. Now, you heard my reaction in the workshop when I first saw the results. It was one of puzzlement. It wasn't what I expected to see. Science tells me that I was not thinking the right way. I mean, you can't deny the facts. They are in front of you. So what we've now got to do is work out what those results actually mean. And I've had to sit down for a few minutes and unravel the problem. It all makes perfect sense when you start putting together some of the factors that I had even overlooked, and I was the person that pointed those factors out to you guys. When you start unraveling the puzzle, it starts to make a lot more sense. So let's go through it a little step by step. Here we've got some parallel rays of light coming in. Now, those rays are passing through the centre. These rays out here are having no effect on what's happening through this green cone here. Normally, when this lens was complete, those rays would focus to this red focal point, which is the nominal focal point. But because I've removed the ability for this lens to focus, those central rays, which are high intensity rays, remember, because they're coming from the peak point, the peak intensity part of the Gaussian curve. Those rays are passing through this very small area of lens at the centre. Now, my proposal was that they are doing just this. They're projecting forward to some additional focal point way beyond the nominal focal point. Let's just take a look at this section of the beam here, the projecting part of the beam. In fact, we go beyond here and we look beyond the focal point as well. When we were doing this test, what we were doing, we were sampling at specific points down this beam. So here's our converging beam, and sure enough, as we went down the beam, we were taking a sample at each one of these positions here, and as you can see, this is the reason why this pattern exists. We get smaller and smaller and smaller as we get further and further down the beam, until we get to a point here somewhere where we reach the minimum focal point just here, and as we lower the table, look, we go through the focal point and the beam gets bigger again. So this is a 2D proof of what we're expecting to see here. But of course, when we convert it into 3D with our piece of acrylic, things don't look quite as simple until you start decoding what you're seeing. Now, the first thing that we see is a fairly large diameter, 1.3mm diameter beam. I've called it 1mm here just for convenience, okay? And it has got a Gaussian distribution. And it has a certain intensity, Y, because of the power that is underneath that curve. Now, I don't know what that power is. That might only be 2 watts. But whatever it is a power that produces a certain level of intense light. As we start moving down the beam, look what happens. The diameter of the Gaussian curve starts reducing. We have not changed the power in that beam. All we've done is reduce the diameter of the Gaussian distribution. As you reduce the Gaussian footprint and keeping the same area underneath the curve, here's what we get. We get a dramatic increase in intensity. So in going from 1mm to 0.1mm, nominally, I'm just mathematically proposing that we've gone from Y to 10 times Y intensity. So we've got much higher intensity beam as we get to these lower positions further down the focus. That explains what's happening to the intensity as we move and sample further down this focusing beam. We're getting higher and higher intensities. But now we have another factor which comes into play, which is time. You've now got to go back to my mode burn pictures, and you see what happens as we have a power and we allow that power to persist for longer and longer and longer. Okay? As we allow more time, the intensity at the center grows like this, and we produce this very sharp spike. So here we are. We've got an intensity which is only Y, okay, which we allow to grow for 300 milliseconds. It's got a wide base, fairly low intensity, but we allow it to grow for a fixed period of time, and it gives us this shape. Now if we go down the beam further and we then allow a smaller diameter beam which has got a much higher intensity, this intensity is now going to start growing like this. It's a mode burn, but it's a mode burn at 0.1mm diameter for 300 milliseconds, as opposed to a mode burn here at 1mm diameter for 300 milliseconds. This one will only produce a very short fat curve, because that's how it starts off. If we allowed this curve to run for a huge amount of time, it would also produce a tall spike. But we're only allowing a fixed period of time for both of these samples to take place. So effectively, what we're looking at in this picture is a strange set of results that are difficult to get your head round initially until you start putting this interpretation on the data. Okay, so here we've got a 50 times magnification of this first little image here. And what we're actually seeing is a mode burn. It's a mode burn that's 1.2 millimeters wide at the top and 300 milliseconds persistence. Now 300 milliseconds is the time taken for every one of these, let's call them mode burns, because that's what they really are. So as we work further and further down, and we drop the table down further, we get to a point here where we've reached the maximum penetration into the material. So that means that we've reached a point down here where there is small enough diameter and long enough persistence of power for the intensity to burrow its way in to this depth. Okay, now we've got the same depth next to it, but in effect what we've got a slightly lower 2 millimeter sample which is running to apparently the same depth. But of course that depth, if we were to correct it as far as distance is concerned, would be 2 millimeters lower. We have just dropped the table by 2 millimeters here, so that one would be 2 millimeters lower than that one, because its diameter has decreased, which means its intensity has increased, but the time has remained the same, so the penetration that's taken place in the same time is more. And then all of a sudden we get to a point where we're reaching that maximum, which is probably close to here, this focal point. And I suspect that that must be somewhere around about here. One of these two will be the focal point. And then after that, what will happen is, you can see it happening here, look, the diameter of the beam is now beginning to grow. And we can go and look at that, if you like, under the microscope. So we count our way in, 1, 2, 3, 4, 5, 6, 7, 7. In fact, look at that one there. Let's go and have a look at that under the microscope. And the interesting thing is, can you see all those little spikes on the outside there? They're almost like little stress cracks that are happening around the outside of the burn. Yep. So that's 1, 2, 3, and 7 is the next one. And 7 is getting thicker than 6. So that must be the focal point there, number 6. And number 7 is now starting to go below the focal point because we're starting to get bigger again. 8, look how quickly it's growing. 9, so there's 12, and as you can see we're coming back to a pretty poor mode burn now. As the diameter of the beam gets bigger below the focal point, we're really getting a very poor, crappy mode burn. As you can see, we're not getting much power and energy into there because look, we've got virtually none of these little stress cracks around the outside. So all of a sudden, when you start dissecting the problem, it shows you clearly what is going on. 38, 40, 42, 44, 46, 48, 50. 52 looks as though it might be starting to grow, but somewhere around about 50 or maybe 52 seems to be the focal point that now exists, which is 12 millimeters beyond the nominal focal point. It looks as though if you were to set this lens at 38, 40, 42, 44, 46, 48, maybe 50 millimeters focal distance, you would be able to cut through 8 millimeter thick acrylic, provided you went slow enough. Now, you may remember a few sessions ago when I used a dummy lens, which was basically a piece of acrylic with a 1.4mm hole drilled through the centre. Now, the hole through the centre of that dummy lens was allowing the maximum intensity of the natural Gaussian distribution to leak through. The amount of damage that it was doing was virtually nothing. So the natural high intensity of the centre of the raw beam is insufficient to do any damage. That small amount of power that leaks through that hole has to be focused to do this amount of damage, 50mm below the lens. You can clearly see from here and the shape of this that the beam is being focused. It's not a collimated beam, it's a focused beam. Hey, I feel like I've just proclaimed that the Earth is not flat, that we live on a globe, or that we are not the centre of our universe, but we're just a little pimple that runs around the sun. I might not get a Nobel Prize for this, but I'm very happy that I've now got a little model in my head that tells me exactly how lenses cut. I just plug it into my little picture of the universe and I'm happy. So, with a big smile on my face, all I can say is thank you for your patience, and I'll catch up with you in the next session.